Let's start with the definition of an antiderivative. To illustrate this definition of antiderivative, let's consider big F as the function defined by 4x cubed plus x squared plus 5. With this, the derivative of f would be 12x squared plus 2x. Thus, if small f would be the function defined by that derivative, which would be now f of x equals 12x squared plus 2x, then small f would be the derivative of that big F. In the same manner, big F would be the antiderivative of that small f. Notice that if we let big G this time to be the function defined by 4x cubed plus x squared minus 17, that function g is still an antiderivative of small f because the derivative of g would be the same thing as 12x squared plus 2x. This is the reason why any function with a function value 4x cubed plus x squared plus whatever that c or constant is would be the antiderivative of f. This is with the consideration, of course, that the derivative of a constant would be 0. Just like what happened here in a big G, although it has a negative 17 there, compared to a plus 5 of our big F, their derivative would be the same, and that would be 12x squared plus 2x. So yeah, that's why we have there plus c at the last part that will represent whatever that constant is, that antiderivative would be just the same. So to formalize and generalize this illustration, we now have these two theorems. And these theorems would assure us that having a plus k or a plus c there at the antiderivative would generalize the antiderivative of a given function. So whenever we use the word antidifferentiation, this would be the process of finding the set of all antiderivatives of a given function. And we are to use this Leibniz symbol to denote the operation of the antidifferentiation. So we can write and read now, the antiderivative of f of x would be the big F of x plus whatever the constant c is. Take note as well of these expressions. And to make this simpler, we can actually consider this. That is, the antiderivative of the derivative of f of x is just the original function f of x plus whatever c is. Let's now have antidifferentiation theorems. Theorem 1.3 asserts us that the antiderivative of 1 dx or dx will just be the same thing as x plus c. To verify antidifferentiation theorem, we just have to apply derivative at the right side of the equation. Just like our x plus c here, if we get the derivative of x plus c, notice that its answer would be 1 dx. Now, if we have a function to be multiplied to a constant a, theorem 1.4 asserts us that we just have to multiply the constant a to the antiderivative of that f of x. We can use theorem 1.5 to get the antiderivative of sum of functions. Now, theorem 1.6 would be the combination of theorems 1.4 and 1.5. And lastly, theorem 1.7 would be for exponentiated expression. That is, if we have an n to be a rational number, and we have to get the antiderivative of x to the power of n, it will just be simply as x to the power of n plus 1 divided by our new exponent this time, which is n plus 1 plus c, with the consideration, of course, that n is not equal to -1. Now we are ready to use these theorems. For our first item, we are to get the antiderivative of 1 over x squared. But notice that we don't have antidifferentiation theorem for division of terms. This gives us a hint that we have to manipulate our given item mathematically so we can get the antiderivative of the given item. So for this item, we are to use law on negative exponent. In case you want to have a review on this law, just click the eye icon there at the upper right corner of your screen and you will be redirected to that video. So with this law, 1 over x squared is the same thing as x to the power of -2. Now it's clear for us that we can actually use theorem 1.7 because we have an exponentiated term. Applying theorem 1.7, the exponent -2 will be added by 1, and our exponent -2 plus 1 will be our denominator this time. And don't forget, we still have plus c there. Simplifying the exponent -2 plus 1, the answer would be a -1. If you want to review with operations on integers, again, just click the eye icon there at the upper right corner of your screen and you will be redirected to that video. So with x in a -1 divided by -1, our answer now would be a -1 over x. Again, x to the -1 will be a 1 over x, which is based on the law on negative exponent. Now how about a negative there? Negative is there because we divided x to the -1 by a -1. And yes, don't forget that we still have plus c there. So the antiderivative of 1 over x squared dx will now be -1 over x plus c. Let's move now to the second item. That would be the antiderivative of the sum of 3x and 5 dx. Clearly, we are to use theorem 1.5 because we are having here a sum of functions. Thus, we now have the antiderivative of 3x dx plus the antiderivative of our second function, which is 5 dx. Keep in mind that aside from distributing the Leibniz symbol for antiderivative, we're also to distribute the dx there. That's why we have there dx for each of the functions. Now, notice that we have constants 3 and 5 there. Gives us a hint that we are to use theorem 1.4. So we have to extract 3 and 5 there. Now we have 3, the antiderivative of x dx, plus 5 times the antiderivative of dx. Don't forget that x is actually an exponentiated term because when we say x, it has an exponent 1. Therefore, we can use this time theorem 1.7. So the antiderivative of x would actually be x squared over 2 plus the constant c1. We have their square for the exponent because the exponent of x1 will be added by 1 and its denominator would be the same exponent this time, which is 2. Don't forget that we are to multiply 3 to the antiderivative of x. That's why we have parenthesized x squared over 2 plus c1. As for the next part, that would be 5 times antiderivative of dx. So using theorem 1.3, antiderivative of dx will just be x plus c. In this case, we are to use c2 for the constant. Distributing now the constants, we'll have 3 times x squared all over 2 plus 3c1 plus 5x plus 5c2. Rearranging the terms, we can now have 3 over 2x squared plus 5x plus c. Indeed, we can generalize the constant here by having c instead of 3c1 plus 5c2. Because anyway, our c's here are constants, so when we multiply the other constants 3 and 5, the answer will still be constants. One way to check if the answer is correct would be getting the derivative of our final answer here. That is, if we get the derivative of x to the power of 5 minus 2x to the power of 4 plus 3x cubed minus x squared plus 7x plus c, we will go back to the given item, which is 5x to the power of 4 minus 8x cubed plus 9x squared minus 2x plus 7. As for the next item, notice that we don't have yet theorem for chain rule of antidifferentiation. Gives us a hint that we still have to manipulate the given item to get the antiderivative of this. So by laws of exponent, square root of x is the same thing as x to the power of 1/2. Now 1 over x is the same thing as x to the power of -1. If you want to be reviewed by laws of exponents, still just click the I icon there at the upper right corner of your screen and you will be redirected to that video. Distributing now x to the 1/2, we'll now have x to the power of 3/2 plus x to the power of -1/2. How come we have 3/2 and -1/2 for the exponents of x? For the benefit of others, let's have a glimpse on how to do laws of exponents here. Distributing x to the 1/2 to the parenthesized terms, we'll have x to the 1/2 times x plus x to the 1/2 times x to the -1. Multiplying with the same base as x here, we have to add the exponents. Thus, adding 1/2 and 1 there would give us 3/2. Similarly, if we are to do the same thing to the exponents 1/2 and -1 there, 1/2 plus a -1 would give us a -1/2. If you want to be reviewed by operations on fractions, still just click the I icon there at the upper right corner of your screen and you will be redirected to that video. Now applying theorem 1.5, we'll now have this. Since we now have exponentiated terms, clearly we are to use theorem 1.7. So adding 1 to the exponent 3/2, we'll now have 5/2. And so the denominator of x to the power of 5/2 will still be 5/2. Similarly, if we are to add 1 to the exponent -1/2, the answer will be a +1/2. And the denominator of x to the 1/2 would still be 1/2. So again, if you want to review operations on fractions, just click the upper right corner of your screen. For the benefit of others, let's have a glimpse on how to do operations on fractions. If we are to divide x to the power of 5/2 by 5/2, we just have to copy the numerator x to the power of 5/2, division turns to multiplication, and we are to get the reciprocal of our denominator, which is 5/2. So 5/2 will become 2/5. And so we now have 2 times x to the power of 5/2 all over 5, or the same thing as 2/5 times x to the power of 5/2. Similarly, we have 2 times x to the power of 1/2 from x to the power of 1/2 all over 1/2. Observe that the given item is actually in terms of radical. Therefore, we may have the final answer to be in radical form. For the benefit of others, this is how we have radical form from fractional exponents. That is, if we have an improper fraction for the exponent, just like 5/2 here, we have to have its mixed form. So still, we have suggested video there at the upper right corner of your screen. Mixed fractions is being discussed there. Notice that 2 and 1/2 is the same thing as 2 plus 1/2. So by law of exponent, this is the same thing as x squared times x to the power of 1/2. As discussed earlier, when we are to add exponents, we are actually multiplying with the same basis. And yes, x to the 1/2 is the same thing as square root of x. So there you go. But how about if we have this? Don't worry, we can actually decompose the fractions. That is, this is the same thing as this. Then simplifying the exponents, we'll have this. If you were either curious or confused on how come we have these exponents right here, I am advising you to really watch those suggested videos first on operations of integers, operations on fractions, and loss of exponents. As what we discussed earlier on division of fractions, t to the power of 5/3 divided by 5/3 would become this. Similarly, t to the power of negative 1/3 divided by negative 1/3 would become this. Upon distributing 5, this would happen. And distributing 7 will have this. And so the antiderivative of item number 5 would be this. I'll be having as well chain rule for antidifferentiation and trigonometric functions, so don't forget to subscribe to be updated.